Good morning, everyone. Welcome to all. Today, we are going to discuss about the microprocessor. Firstly, we are going to get ourselves familiar with how a computer is formed or how a desktop PC is formed. A computer is a programmable machine that receives input, stores and manipulates data or information, and provides output in a useful format. We'll be having different components of the computer as shown in the picture. This is the basic block diagram of a computer, which consists of a CPU, memory, mainly RAM and ROM, input-output unit. The basic component of a microcomputer also comprise of a CPU, that is the central processing unit, which does the portion of a computer system that carries out the instruction of a computer program, primary element carrying out the computer's functions. It is the unit that reads and executes program instructions. The data in the instruction tells the processor what to do. You can see the pictorial representation of Pentium D dual core processors. Memory. Physical device used to store data or program sequences of instructions is called as program on a temporary or a permanent basis for use in an electronic digital computer. A computer main memory comes in two principal varieties: random access memory and read-only memory. RAM can be read and written to any time the CPU commands it, but ROM is preloaded with data and software that never changes, so the CPU can only read from it. ROM is typically used to store the computer's initial startup instructions. In general, the contents of RAM are erased when the power to the computer is turned off, but ROM remains its data indefinitely. In a PC, the ROM contains a specialized program called the BIOS that orchestrates loading the computer's operating system from the hard disk drive into RAM whenever the computer is turned on or reset. Input output unit refers to the communication between information processing systems such as computer and the outside world, possibly a human or another information processing system. Inputs are the signals or data received by the system, and outputs are the signals or data sent from it. Devices that provide input or output to the computer are called peripherals. On a typical personal computer, peripherals include input devices like the keyboard and mouse, and output devices such as display and printer. Hard disk drives, floppy disk drives, and optical disk drives serve as both input and output devices. Computer networking is another form of input output interfacing. The data size is nothing but the data that can be handled by a particular microscope. Nibble means 4-bit. You can see the 4-bit allocation. Byte 8-bit, you can see the 8-bit allocation for data. Word as 16-bit allocation for the data. The sign bit is the 15th bit and 0 byte at the beginning. Long word consists of 32-bit and so on. Fetching and execution cycles. Fetching cycles. The fetch cycle takes the instruction required from the memory, stores it in the instruction register, and moves the program counter on one so that it points to the next instruction. Execute cycle. The actual actions which occur during the execute cycle of an instruction depend on both the instruction itself and the addressing mode specified to be used to access the data that may be required. Fetching an instruction. Step 1. Instruction pointer, that is the program counter, holds the address of the next instruction to be fetched. In the diagram, you can see the instruction pointer 0001 with the address bus is pointed at the memory location. The contents of that 0001 location is OFF. As the instruction of fetching instruction is continued in the step 2, instruction pointer is going to direct to the address bus. Okay, the contents of the program counter are passed across the address bus. Now the instruction pointer has passed the data to the address bus. Now the address bus is going to set that particular data into memory access register. Now, the memory location of the next instruction is located from the memory access register to the memory location. Then fetching an instruction is continued. The contents are put on the data bus. The memory location 0001 consists the content of OFFF is being transferred to data bus. Now, from the data bus, the whatever the fetched commands or opcodes OFFF is being transferred to the instruction register. Internal structure and basic operation of a microprocessor. Microprocessor consists of ALU register section, control and timing section, which is being interfaced with address bus, data bus, and control bus. This represents the basic block diagram of a microprocessor. Arithmetic and logic unit, the component that performs the arithmetic and logic operations, the most important components in a microprocessor and is typically the part of the processor that is designed first, able to perform the basic logical operations like AND, OR, NOT, NAND, etc., including the addition operation. The inclusion of inverters on the inputs enables the same ALU hardware to perform the subtraction operation, that is adding and inverted operand, and the operations like NAND and NOR can also be handled. Control unit, the circuitry that controls the flow of information through the processor and coordinates the activities of the other units within it. In a way, it is the brain within the brain, as it controls what happens inside the processor, which in turn controls the rest of the PC. On a regular processor, the control unit performs the task of fetching, decoding, managing, execution, and then storing results. The internal structure of control unit, that is the clock, counter clock, that is the control step counter, then it is been passed on to step decoder, from there to encoder. The instruction decoder from the IR registry is going to place the data on the encoder. From the encoder, it is being sent to the control inputs. The control signals are fed to the control bus, and also the status facts and condition codes are fed into the encoder. Register sets. The register or section array consists completely of circuitry used to temporarily store data or program codes until they are sent to the ALU or to the control section to memory. The number of registers are different for any particular CPU, and more registers a CPU have will result in easier programming tasks. Registers are normally measured by the number of bits they can hold, for example, an 8-bit register or a 32-bit register. Accumulator, a register in which intermediate arithmetic and logic results are stored, is called as accumulator. The example for this accumulator is summing a list of numbers. The accumulator is initially set to 0, then each number is added to the value in the accumulator. Only when all the numbers have been added in the result held in the accumulator return to the main memory or to another non-accumulator CPU register. So condition code register CCR is a 8-bit register used to store the status of CPU such as carry, 0, overflow, and half carry. These are the different condition code registers, that is Z indicates 0 flag, indicates that the result of a mathematical or logical operation was 0. Carry flag is denoted by C, indicates that the result of an operation produced an answer greater than that number of available bits. This flag may also be set before a mathematical operation as an extra operand to certain instructions, example add with carry. Capital X is the extend flag, masks the XIRQ request when set. It is the hardware. Okay, it is set by an hardware and clear by the software as well. Is set by an unmaskable XIRQ. Capital N negative sign flag indicates that the result of a mathematical operation is negative. In some processors, the N and S flags have different meanings. The S flag indicates whether a subtraction or addition has taken place, whereas the N flag indicates whether the last operation result is positive or negative. V is overflow flag, indicates that the result of an operation has overflowed according to the CPU's word representation, similar to the carry flag but for signed operations. Capital I is the interrupts. Interrupts can be enabled or disabled by respectively setting or clearing this flag. Modifying this flag may be restricted to programs executing in a supervisor mode. Program counter, a 16-bit register used to store the next address of the operation code to be fetched by the CPU. Not much used in programming, but as an indicator to user only. Purpose of PC in microprocessor: to store address of the top of stack, to store address of next instruction to be executed, count the number of instructions, to store base address of the stack. This is the internal structure of program counter, how that particular program is been counted and been made available for the next immediate execution. Stack pointer: a stack is configured as a data structure that grows downward from high memory to low memory. At any given time, the SP, that is the stack pointer, holds the 16-bit address of the next free location in the stack. The stack acts like any other stack when there is a subroutine call or an interrupt, that is pushing the return address on a jump and retrieving it after the operation is complete to come back to its original location. Bus system: a bus system that transfers data between computer components inside a computer or between the computer is pictorically demonstrated. This picture shows four PCI Express bus card slots from top to bottom: X4, X16, X1 and X16, compared to a traditional 32-bit PCI bus card slot very bottom. Bus system connection: here you can see the bus system is connected to each and every part of a microcomputer. CPU or a microprocessor, which consists of ALU, internal communication registers, temporary storage or control section, is been interfaced with storage input external memory, that is your floppy disk drive, hard disk drive, CD-ROM drive, magnetic tape, etc., which is in turn been uh, interfaced in the two-way communication with input interfaces like keyboard, mouse, joystick, scanner, printer, etc., light pen, etc., with an output interface, the monitor and printer. The input is interfaced with the storage of the internal memory, that is the RAM. ROM is read only, which is been interfaced with your output interface. This is the bus connection, that is the bus cables, how it is been connected to different parts of the microcomputer. Data bus: the data bus is bidirectional. Data or instruction codes from memory to input or output are transferred into the microprocessor. The result of an operation or a computation is sent out from the microprocessor to the memory or input output. Depending on the particular microprocessor, the data bus can handle 8-bit or 16-bit data. Address bus is a unidirectional one over which the microprocessor sends an address code to a memory or an input output device. The size or the width of the address bus is specified by the number of bits it can handle. The more bits there are in the address bus, the more locations a microprocessor can access. A 16-bit address bus is capable of addressing 65,536, that is 64K addresses. Control bus is used by the microprocessor to send out or receive timing and control systems in signals in order to coordinate and regulate its operation and to communicate with other devices, that is memory or input output devices. Microprocessor clock, also called as clock rate, the speed at which the microprocessor executes instructions. Every computer contains an internal clock that regulates the rate at which the instructions are executed and synchronizes all the various computer components. The CPU requires a fixed number of clock ticks or a clock cycles that we can call to execute each instruction. The faster the clock, the more instructions the CPU can execute per second. The clock speeds are expressed in terms of megahertz, mHz, or gigahertz, GHz. Some microprocessors are superscalar, which means that they can execute more than one instruction per clock cycle. Like CPUs, expansion buses also have clock speeds. Ideally, the CPU clock speed and the bus clock speed should be the same so that neither component slows down the other. In practice, the bus clock speed is often slower than the CPU clock speed, which creates a bottleneck. This is why new local buses such as AGP have been developed. Examples of microprocessors: Intel 8085 and Intel 8086 are the classic examples of microprocessors. Intel 8085 microprocessor is been pictorially demonstrated. It is an 8-bit microprocessor introduced by Intel in the year 1977. It was binary compatible with the more famous Intel 8080, but required less supporting hardware, thus allowing simpler and less expensive microcomputer systems to be built. In 8085 microprocessor, the modification is made, and the 8086 is a 16-bit microprocessor chip designed by the Intel, which gave rise to the x86 architecture development work on the 8086 design started in the spring of 76, and the chip was introduced to the market during the summer of 1978. The Intel 8088 released in 79 was slightly modified chip with external 8-bit data bus, allowing the use of a cheaper and fewer supporting logic chips, and is notable as the processor used in the original IBM PC. Thank you.